This axe head has been sitting outside behind the shed for months. Rain, humidity, cold mornings, hot afternoons. By the time I picked it up again, the entire surface had turned that familiar rough orange color. The kind of rust that makes you think the metal underneath is already halfway gone. Most people see something like this and think the only solution is to grind it down, sand it clean, or coat it with some kind of paint or oil. But instead of removing the rust, I'm going to do the opposite. I'm going to use the rust itself. Right here in this container is a simple mixture that costs about $3 to make. No special equipment, no expensive chemicals, just a reaction that blacksmiths, museum conservators, and metal workers have quietly relied on for centuries. Watch what happens. The moment the solution touches the rust, the color starts to change. That bright orange corrosion begins turning dark gray, then deeper, almost blue-black. What you're seeing isn't the rust being cleaned off, it's the rust transforming. In less than an hour, the same corrosion that was slowly destroying this piece of metal will become a protective layer bonded directly to the surface. Not paint, not a coating, but a chemical conversion that turns rust itself into armor. And the strange part is, this reaction has been known for over 200 years, yet almost nobody today has ever heard of it. Now, if this reaction works the way it looks like it does, a reasonable question is why almost nobody talks about it. Because rust is big business. Every year, corrosion quietly destroys enormous amounts of metal. Car frames, brake lines, exhaust systems, farm tools, outdoor equipment, fences, machinery parts, the list is endless. Entire industries exist around repairing, replacing, and preventing rust damage. The global automotive parts market alone is worth hundreds of billions of dollars. A large portion of that comes from components that fail earlier than they should because corrosion slowly eats away at them. Replacement parts, protective coatings, rust removal products. All of it adds up to a massive industry built around the idea that rust must always be removed, sanded away, or covered with expensive treatments. But the chemistry I'm about to show you follows a completely different idea. Instead of fighting rust, you convert it. You take the unstable orange iron oxide that keeps spreading and transform it into a stable compound that bonds to the steel and protects it from further corrosion. And once you understand that principle, rust stops looking like a problem. It starts looking like raw material waiting for the right reaction. What's interesting about this reaction is that it wasn't discovered in a modern laboratory. Different cultures figured it out independently, long before chemistry had formal names for the compounds involved. Roman metalworkers noticed that iron tools stored near oak bark tanning vats seemed to darken instead of rusting away. Leather tanners worked with oak bark extracts rich in tannins, and over time they realized that iron exposed to those same plant compounds developed a dark, protective surface. Centuries later, Japanese swordsmiths observed a similar effect using plant-based acids and fermented fruit extracts while finishing blades. The reaction produced a dark patina that stabilized the steel and helped protect it from corrosion. Across parts of West Africa, traditional iron workers used extracts from acacia pods and tree bark to treat tools before the rainy season. The iron darkened, but it didn't flake apart the way untreated rusted metal often did. These cultures had no shared communication and no modern chemical theory, yet they all arrived at the same practical solution. Iron plus certain plant compounds produced a stable dark surface that protected the metal underneath. It wasn't magic. It was chemistry that anyone paying attention to iron, rust, and plants would eventually notice. And today we know exactly what that chemistry is. What's interesting about this reaction is that it wasn't discovered in a modern laboratory. Different cultures figured it out independently, long before chemistry had formal names for the compounds involved. Roman metalworkers noticed that iron tools stored near oak bark tanning vats seemed to darken instead of rusting away. Leather tanners worked with oak bark extracts rich in tannins, and over time they realized that iron exposed to those same plant compounds developed a dark protective surface. Centuries later, Japanese swordsmiths observed a similar effect using plant-based acids and fermented fruit extracts while finishing blades. The reaction produced a dark patina that stabilized the steel and helped protect it from corrosion. Across parts of West Africa, traditional iron workers used extracts from acacia pods and tree bark to treat tools before the rainy season. The iron darkened, but it didn't flake apart the way untreated rusted metal often did. These cultures had no shared communication and no modern chemical theory, yet they all arrived at the same practical solution. Iron plus certain plant compounds produced a stable dark surface that protected the metal underneath. It wasn't magic, it was chemistry that anyone paying attention to iron, rust, and plants would eventually notice. And today we know exactly what that chemistry is. Even though most people have never heard of this reaction, it never disappeared completely. It quietly survived in places where metal objects need to last for generations. Museum conservation labs still use tannin-based treatments when stabilizing corroded iron artifacts. When archaeologists recover iron tools, weapons, or hardware from historical sites, they often face the same problem. Removing the rust completely can damage the object, but leaving it untreated allows corrosion to continue. So instead, conservators convert the rust. The same tannin reaction forms a stable ferric tannate layer that stops the corrosion process and preserves the artifact for long-term storage. The Canadian Conservation Institute, for example, still lists tannic acid treatment as a standard method for stabilizing corroded iron. Blacksmiths also continue using similar techniques when restoring antique tools. Rather than grinding away the surface and losing metal thickness, they convert the rust and keep the original shape intact. In other words, the chemistry is not experimental. It's already trusted in environments where objects are expected to survive decades or even centuries, and the same reaction can be done in a simple container using ingredients that cost just a few dollars. The surprising part about this method is how simple the materials are. You don't need specialized equipment or rare chemicals. Everything can be found online or at a hardware store, and the total cost is only a few dollars. The main ingredient is tannic acid powder. This is simply the purified form of the same tannins found naturally in plants like oak bark and tea leaves. A small bag usually costs between $3 and $5 and lasts for dozens of treatments. The second ingredient is phosphoric acid. You'll often find it sold in hardware stores as navel jelly or rust remover gel. This helps the solution penetrate deeper into the rust layer and stabilizes any remaining corrosion. Next is distilled water. Using distilled water matters because tap water often contains chloride ions, and chloride can accelerate corrosion over time. Finally, you only need a few simple tools: a wire brush or steel wool to remove loose rust, and a foam brush or cloth to apply the solution. That's it. A small amount of powder, a little water, and a brush, and you have the same chemistry used by museum conservation labs. Once you have the materials, the preparation is simple. Start by mixing about 4 grams of tannic acid powder into 100 milliliters of warm distilled water. Warm water helps the powder dissolve faster. Stir it slowly until the solution turns the color of strong black tea. At this point, the mixture already works on its own, but adding a small amount of phosphoric acid improves the reaction. A teaspoon of navel jelly or phosphoric acid solution is enough. Stir it in until everything blends evenly. The liquid will remain a dark tea-like color. That's the entire formula. Before applying it, take a wire brush or some steel wool and remove any loose, flaky rust from the metal surface. You don't need to sand the metal down to bare steel. In fact, that would defeat the purpose. The reaction needs existing rust to work. Once the surface is brushed clean of loose debris, apply the solution evenly using a foam brush or cloth. Within about 10 to 15 minutes, the orange rust begins changing color. First dark gray, then deep blue-black. That color shift is the conversion happening in real time. Once the first coat is applied, the most important step is simply letting the reaction finish. As the solution dries, the tannins continue binding with the iron oxide on the surface. Over the next couple of hours, the rust layer slowly converts into ferric tannate, that dark blue-black coating you saw forming earlier. Give it 2 to 4 hours to dry completely. At that point, you can apply a second thin coat of the solution. Conservation research actually recommends several thin layers rather than one thick one. Thin coats penetrate the rust better and build a denser protective layer. After the second coat dries, the metal should appear noticeably darker, almost like a natural patina rather than paint. That's exactly what you want. The surface shouldn't look glossy or coated. It should look like the metal itself simply changed color, because in a way it did. The unstable rust has now been chemically reorganized into a stable compound that protects the steel underneath. And once that conversion is complete, you can add an optional finishing layer depending on how the metal will be used. At this point, the rust has already been converted into ferric tannate, which is stable and far less reactive than ordinary rust. For many tools, that layer alone significantly slows future corrosion. But depending on how the metal will be used, adding a final protective finish can extend its lifespan even further. For outdoor tools like axes, shovels, or garden equipment, a light coat of boiled linseed oil works well. It soaks into the surface and creates a moisture barrier while keeping the metal looking natural. Some people prefer beeswax, gently warmed and rubbed into the surface. It forms a thin protective film that repels water while still allowing the metal to breathe. For vehicle frames or metal exposed to road conditions, something stronger like a rubberized undercoating spray can be applied after the conversion layer dries. And if you're working with cast iron cookware, the final step is simply reseasoning the surface in an oven, just like normal cast iron maintenance. In every case, the ferric tannate layer becomes the foundation. The finish simply adds another barrier against moisture and oxygen. There's one honest thing worth saying before we finish. This method doesn't make metal completely immune to corrosion forever. In extremely harsh environments, heavy road salt, constant ocean spray, or long-term chemical exposure, even a ferric tannate layer will eventually degrade. But in normal conditions, it slows corrosion dramatically. For most tools and equipment, a quick touch-up once a year is more than enough to keep the metal stable. And when you step back and think about it, the interesting part isn't just that the reaction works, it's that this knowledge used to be common. Blacksmiths, leather workers, and metal craftsmen passed techniques like this down through generations. Long before hardware stores sold shelves full of rust products, people understood how certain plant compounds reacted with iron. Then over time, as industrial coatings and branded chemicals became the standard, the older knowledge simply faded from everyday use. The chemistry didn't disappear, it just stopped being talked about. And that's what I find fascinating about reactions like this. They remind us that sometimes the simplest solutions have been sitting quietly in the background for centuries. $3, 45 minutes, and the rust that looked like a problem becomes part of the protection. That's it for today, and I'll see you in the next one.